All right, so first let's get a general solution, then we'll get a particular solution. So let's ignore that for the time being. To solve the differential equation. Now normally we would have written this as dH dt, right? Because the function would be named h and the variable is t. And then if we had it that way, we would multiply both sides by dt. So that's how I get the dt over here. And I could call that just h, but I'm just going to keep calling it h of t. Because look, I'm cheating a little bit. Let me go backwards. Didn't all our differential equations work out the same way? All right, like we start with this, and then don't we end up with y on one side, and then the integral of whatever it was they gave us, dx, or in this case dt, on the other side? And doesn't that happen every time? It happens there, it happens there, it happens there, there. That's what's going to happen. All right? All right, so since I know that's what's going to happen, I'm going to use that. So I'm going to get the function on the left and then the integral of the derivative, right? That's the derivative. The integral of the derivative, dx, or in this case dt, on the other side. So since I realized that's what always happens, that's what I wrote down. Are you with me on that? Okay. Now, find the antiderivative. Use the power rule. Use the power rule for indefinite integration. So we add 1 to the exponent, makes it a t to the 4th. Then we divide our coefficient by that new exponent. 8 divided by 4 is 2. So we get 2t to the 4th. Then for 5, we just got to, actually it is the power rule too. You could think of that as 5t to the 0, because t to the 0 is 1. 5 times 1 is 5. Add 1 to the exponent. Now it's a 1. Divide your coefficient by that new exponent. 5 divided by 1 is 5. Plus c. That gets us here. That is the general solution of the differential equation. To get the particular solution, you will be given some more information. The other information you're given are called initial conditions, because it's just things that you know initially, okay? Not necessarily at time 0, but just things you know. They're always called initial conditions, even if it's not time 0. So just things you know. So things we know. We know that h of 1 equals negative 4. That means whenever t equals 1, the function equals negative 4. So we just found the function, replace t with 1. So instead of 2t to the 4th, that's 2 times 1 to the 4th. Instead of 5t, it's 5 times 1. And whenever we do that, the function itself, h of t, equals negative 4. So it's just substitution. You with me? Okay. Simplify. 1 to the 4th is 1. 2 times 1 is 2. 5 times 1 is 5. So we have negative 4 equals 2 plus 5 plus c. Well, 2 plus 5 is 7. And if I subtract 7 from both sides, I get negative 11 equals c. So guess what I can do now? I go back to my general solution, replace c with what we now know it equals. It equals negative 11, and I get the particular solution. So here's what you need to know for future reference. This is the general solution when you still have the plus c. Use initial conditions to solve for c. Once you know what c is, you can get the particular solution. Now, the reason it's called particular is back just a few problems ago when we were given a derivative and we would draw two different functions that had that derivative, there's just one that has this derivative and this condition. So it's a particular answer now. If we changed our condition to h of 1 equals 10, guess what? We'd get a different particular solution. We'd have the same general solution, but we'd get a different particular solution. So the particular solutions, you're getting to, of all those different functions that have that as the antiderivative, you get the particular one that has that condition as well. Okay? All right, what else? All right, on 61, let's see. We're still doing the same thing. So let's take a look here. All of this is the problem. We start with the second derivative equals x to the negative 3/2. Then they give us a little bit of information about the first derivative. They tell us what the first derivative equals when x equals 4. And then they tell us a little bit of information about the function itself. The function equals 0 when x equals 0. So this one's going to take a while. Here's what we do. If I take the antiderivative of the second derivative, that's the first derivative, right? So the first derivative equals the antiderivative of x to the negative 3/2 and then dx. Okay? So you with me at the first check mark? So let's actually find the antiderivative. So f prime of x equals, add 1 to the exponent, so negative 3/2 plus 1 is an exponent of negative 1/2. Divide your coefficient by negative 1/2. Dividing by negative 1/2 is the same thing as multiplying by the reciprocal of negative 1/2. So multiply by negative 2 plus c. Now, I called it C1 because I've done these problems before, and I know that I'm getting ready to have to solve another differential equation in just a second. Okay? So I'm going to have a different C in a minute. So I called that one C1 so I can differentiate it from the C I'm going to have in a minute. Now, use the information they gave us about the first derivative. F prime of 4 equals 2, so that means that the derivative equals 2 whenever x equals 4. So, make the derivative equal 2 when x equals 4. Then we can solve for C1. So 4 to the negative 1/2 is the same thing as 4 to the 1/2 in the denominator. 4 to the 1/2 in the denominator, same thing as the square root of 4 in the denominator, which is the same thing as 2 in the denominator. So I had a negative 2 over that, so I get negative 1. Add 1 to both sides, and now we know what C1 equals. Substitute it back in, and now we know the particular solution for the first derivative. So we went from the general solution for f prime of x to the particular solution for f prime of x. Now, we get to do the whole thing over again to get f of x. So, take the indefinite integral, the antiderivative of both sides. I'm going to get the antiderivative of f prime will be f. And on the other side, I'm going to have to figure out what the antiderivative of negative 2 x to the negative 1/2 plus 3 dx is. So, let's see what it is. Add 1 to the exponent. So if you have a negative 1/2 and you add 1 to it, you get a positive 1/2. Divide your coefficient by the new exponent. So dividing by 1/2 is the same thing as multiplying by 2. So the coefficient of negative 2 times 2 is negative 4. So I get that. The antiderivative of 3 is 3x plus c. I called this one C2, but you can't guess why I called it C2. Because it's the second C. All right? So what we have now is we have the general solution for f of x. Let's get the particular solution for f of x. So use the condition they gave us that f of 0 equals 0. So that means the function equals 0 whenever x equals 0. So the function equals 0, x equals 0. Solve it for C2. C2 equals 0. So that gives us the particular solution for f of x. Well, that was fun, right? Good time had by all. All right, then we do 62 the same way. It's just that it's got a trig function in it. So I'm going to go a little faster through this one. Well, maybe I will. We'll start with the second derivative. We start with this and this as our conditions. So the antiderivative of the second derivative is the first derivative. Then we've got to figure out the antiderivative on the other side. And I know right now you don't really have a good reason for putting that dx there other than I'm telling you to. We will. We will have an excellent reason for that dx later. Okay? So keep putting the dx there. All right? And then we just look up what the antiderivative of the sine of x is. It's negative cosine of x plus c. Are you getting any of those trig antiderivatives memorized yet? You need to. I mean, work on it. You don't have to have them this second, but work on it because that's going to really slow you down in the future if you don't know those. All right, so we've got the general solution for f prime of x. Use what you know about the derivative to find the particular solution for f prime of x. Wow, I was like Captain Kirk there with the emphasis on each syllable. Y'all need to watch more Star Trek if you don't get that. Okay, so f prime of 0 equals 1. What's that? Is he working on lowering his grade? Is that what's going on? So the derivative equals 1 whenever x equals 0. All right, so the cosine of 0 is 1, so negative cosine of 0 is negative 1. Add 1 to both sides. Now we know what C1 equals, and now we get the particular solution for f prime of x. You follow me on the first half of this problem? Yes, no, maybe. Lots of yeses. All right, we do it all again. The antiderivative of f prime of x is f of x. We'll have to figure out what the antiderivative of negative cosine of x plus 2 dx is. Copy down the negative sign, and then the antiderivative of cosine is sine. So I get negative sine of x. The antiderivative of 2 is 2x plus c. Call this one C2. Use the information we're given. So whenever x equals 0, the function equals 6. And let's see, 2 times 0 is 0. Sine of 0 must be 0, and negative 0 is 0, and 0 plus 0 is 0, and 0, and then a 0. And so then C2 is 6, which gives us the particular solution that we were after. Ta-da! Thank you. All right, turn to page 256 in your book. 256. Slope fields. All right, be quiet. Slope fields will definitely, for sure, be on the AP test, at least in 2 different questions. All right? In exercises 49 through 52, a differential equation, a point, and a slope field are given. A slope field, also called a direction field, consists of line segments with slopes given by the differential equation. These line segments give a visual perspective of the slopes of the solutions of the differential equation. All right, so let's just look at the slope field first. All right, what that is it's a way to figure out what the function is going to look like without knowing anything else about it. Because sometimes we know rates instead of functions. Okay? For instance, we might know that the velocities of moving objects as opposed to the position function for the moving object. All right? So if we can chart the velocities at different times, different distances, whatnot, then we can get the velocities are, remember, velocities are derivatives, derivatives are slopes, so we can get all those little blue slopes. Don't think of the blue segments as anything except telling you what the slope equals. Okay? And then you just can kind of fit your curve to that. So let's see. What number is this one? dy dx equals cosine. Yeah. So this was number 51. All right. So without doing the problem, I can figure this out by trying to follow the slopes. I can do something like the graph of the solution is going to look something like that without the little mistakes. Okay? If I started up here, well, or down here, I'd get a similar looking graph. So that's what a slope field can do for you. Okay? Eventually we'll make our own slope fields. Sometimes they're really, really easy. Sometimes they're really, really difficult. Depends on how difficult the differential equation is. But for now, we're taking their slope field and we're trying to graph solutions. So, part A, sketch two approximate solutions of the differential equation on the slope field, one of which passes through the indicated point. Oh, wish I'd have read that part. Okay, passes through the indicated point. Something like that. Okay, so I'm an overachiever. I did 3, one of which passes through the indicated point. So I've done part A. Part B, use integration to find the particular solution of the differential equation and use a graphing utility to graph the solution. And then compare the result with the sketches in part A. I'm so confident in my sketches of part A, I'm not even going to do that. I'll let you do it, but I'm not going to do it. So we've done part A. Now part B is just do what we've always done. All right? Solve the differential equation. So our differential equation is dy dx equals a cosine of x. And then think of that 0.04 as being an initial condition. They're telling you that for the solution, whenever x equals 0, y equals 4. All right, so we know that we can multiply both sides by, let's skip down to the chase. We're going to get y on the left, and we're going to get the antiderivative of the cosine of x dx on the right, aren't we? So the antiderivative of the cosine of x dx is sine of x plus c. So that's our general solution. Now we've got to get our particular solution. Use the 0.04 to get the particular solution. So whenever x equals 0, y equals 4, and then we solve for c. We now know that c equals 4. So y equals the sine of x plus 4 is our particular solution. That means that this one, the one that went through the point, is the graph of y equals the sine of x plus 4. This other one is the graph of y equals the sine of x plus a different c. Go back up to here. That's y equals the sine of x plus 4. That's y equals the sine of x. I wrote c. Sine of x plus c1. That's y equals the sine of x plus c2. And then for however many of them you feel like making. All right? Questions on slope fields? All right. Let's see. Let's do, we haven't done 68 yet, have we? Let's do 68. Vertical motion. In exercises 67 through 70, use A of t equals negative 32 feet per second as the acceleration due to gravity. And we're going to neglect air resistance, which is always a little iffy when you neglect air resistance because it's a real force, okay? So anyway, neglecting air resistance. So 68 says, show that the height above the ground of an object thrown upward from a point s0 feet above the ground with an initial velocity of v0 feet per second is given by this function. F of t equals negative 16t squared plus v0t plus s0. All right. Now, remember how this works? You've got a position function. If you take its derivative, you get the velocity function. If you take the derivative again, you get the acceleration function. Now, we can turn all that around. If I take the antiderivative of acceleration, what do I get? Velocity. And if I take the antiderivative of velocity, what do I get? Position. Okay? All right, so if I know that A of t equals negative 32 feet per second squared, if I take the antiderivative of acceleration, I get the velocity. So the velocity equals the antiderivative of negative 32 dt. What is the antiderivative of negative 32 dt? All right, but let's use t because it's time. But negative 32x plus c1, or negative 32t plus c1. Now, they told us that the initial velocity is v0. That means the velocity when t equals 0 is to be called v0. So v of 0 equals v0, therefore, and then replace. So your velocity equals v0 whenever t equals 0. So replace v of t with what it's supposed to equal when t equals 0, v0, and then replace t with 0. Well, negative 32 times 0 is 0. That means that c1 can be replaced by v0, which means the particular solution of the velocity is this. And I know you're probably thinking, how's that particular if it's still got a constant that we don't know in it? Well, it is, because that's what they gave us as the initial velocity. And in fact, that v0 is sort of unknown now, but don't we know? Well, I'll stop there. Okay? Do the same thing again, and I'll end up with the position function, won't I? Take the antiderivative of both sides. The antiderivative of velocity is position. Then the antiderivative of negative 32t plus v0 dt, I'm going to have to figure out. If you're dropping it, it is. If you're throwing it, it'll have force to it. All right, so the antiderivative of negative 32t is negative 16t squared. The antiderivative of v0 is v0t. I don't know what v0 is, but I know it's a number. So it's v0t plus c2. So now I've got the general solution for the position function. What's our initial position? S0. So S of 0 equals S0. So equals negative 16 times 0 squared plus V0 times 0 plus C2. That means S0 equals C2, and that is our particular solution. The directions for this problem said, show that. Did we just show that? All we got to do is call it F instead of S, and we showed what they told us to show. And if they don't think we showed it, we go, see? Oh, come on, that deserved a smile. All right, let's see. Was that in the last assignment, 62? That was yesterday? Ooh, that means 70 is the only one left. Uh-oh, not much time. Yeah, I think we'll start with 70 tomorrow.